Hi, now let's continue with Boltzmann machines. In the previous sub-lecture, we saw that Hopfield networks are types of neural networks that are associated with a quadratic energy function. And this energy function couples every neuron in the graph with every other neuron. Boltzmann machines can be viewed as a stochastic variant of Hopfield networks, and specifically Boltzmann machines, neurons in Boltzmann machines respond with either +1 or -1 according to sigmoid probability fed by the activation received from all other neurons. One could say that the Boltzmann machines implement the Gibbs sampling for the PDF governed by the quadratic energy function. One problem that Boltzmann machines have is that they are very parameter heavy. In fact, their number of parameters scales up quadratically with the number of dimensions of the visible unit. So you can imagine that if I have a relatively small image of only 256 by 256 pixels, this would basically amount to roughly 4 billion parameters just for a single layer. That is clearly not feasible, not practical, not desirable. What is more, Boltzmann machines do not learn features. They don't have latent variables which we can train them such that they represent, they capture specific patterns in the data. So what we can do is we take a Boltzmann machine. However, instead of connecting all visible units with all visible units, we introduce a second group of variables, latent variables, and then we connect the visible units with all latent variables and vice versa, but we don't have connections between visible variables or between latent variables. This yields still a quadratic energy function, now connecting every visible variable with every latent variable. This quadratic term, therefore captures correlations between our latent features and our inputs. The two unary terms can be viewed as capturing primers on our inputs and on our latent values. So basically, how much should the prior information, whether a pixel is 1 or -1, influence the final state of our neural network. So restricted Boltzmann machines are governed by the quadratic energy function, and the problem now is, however, that they don't really have the form of an energy-based model, in the sense that in the denominator now we don't have a single exponential but a sum of exponentials, and we have the sum of exponentials because we have to integrate out the latent units. We have to integrate them out because we don't really know what is the right latent variable. There is no right latent variable for our input. We have a distribution of latent variables. So that we bring the Boltzmann machine, the restricted Boltzmann machine, into a familiar and comfortable energy-based form, like with an exponential over a partition function, we can rewrite the numerator and the denominator in terms of a free energy function, and then everything is peachy again. Restricted Boltzmann machines comprise graphs, bipartite graphs, that is, graphs whose two groups of variables connect with each other, but not within each other. And their connections are undirected. So this means that the flow, the information flows from both forward and backwards. This means that inference has to flow and evaluation has to flow both ways. For restricted Boltzmann machines, for that model, we have to define the hidden variables as being independent, conditioned on the visible variables, and vice versa, the visible variables are independent condition of the hidden variables. This is a design choice with certain advantages and disadvantages that we will see later. Clearly, when we assume that the visible dimensions, the visible variables x, are independent with each other, that is not a realistic, perhaps, assumption, in the sense that we do know that neighboring pixels, for instance, do depend on each other. However, it's a choice that will help us scale up learning and optimization. What is missing now is how do we model our conditionals that we just described. So the conditional probabilities are defined as by sigmoid nonlinear activation functions. These receive as input the weights times the visible or the latent units, and these are Bernoulli probabilities from which we can sample our binary variables. Since the RBMs are bidirectional, this means that we have no single forward propagation. We rather have to go back and forth. So given our initial pixel values, we sample a latent vector, right? So an instantiation for our latent vector. Then based on our latent vector, we can sample new pixels, so a new image, right? In a way we're reconstructing the image. Then based on our reconstructed image, we can sample new latent variables and so forth. This is why we've got information flow forward and backward. Now, to train any energy model, since RBM is also an energy model, we're going to discuss a bit more generally here. The reasonable thing to do, or one of the reasonable things to do, is to maximize the log likelihood as usual. So basically, we take the sum of the logarithm of the probabilities. This here can be rewritten in terms of the nominator and the denominator of our probability density function. So this can be written down in terms of the expected value over the minus energy minus the logarithm of the partition, right? So since p of theta is simply the exponential over z, by taking the logarithm of p of theta, then logarithm xp and whatever is inside the exponential minus the logarithm of z. That's simply it. And here we're taking into account the fact that averaging equals expectation, as we'll see next. P0 here stands for the data distribution. So basically it means when I say I'm sampling from my P0 or from the data distribution, it means I simply take a random image from my training set. This is it. If I take the gradients of this energy model, and now we focus only, so not on the sum of all possible training inputs, but just one, so just single x, just single image, then I'm not going to go through all the math, but I've written down for your convenience. However, we can show that this basically corresponds to the derivative of the energy function, well, minus the derivative of the energy function plus the derivative of the energy function after we sample images and taking the average over that. So here again I am writing down this identity that the sum of a function times the probability distribution function of the input of that function equals to the expected value, right? So we can do this switch nicely, and what this as we'll see next and also in another lecture, what is convenient about that is that we can then approximate this quantity by a sampling procedure. Putting now this more into the RBM context, if you have an RBM, we have latent variables. So this means that our logarithm here has to integrate out all the latent variables. And then by repeating the same process, we obtain a very similar quantity here. So instead of having just the energy function, now we're going to have to average over our latent variables so that we integrate them out. And here again, our normalization constant does not depend only on summing over all possible images x prime, but also all over our latent variables. So since for an RBM we have a very specific type of energy function, so the quadratic in a quadratic form, taking the derivatives with respect to any parameter is straightforward. It simply corresponds to the multiplication of the ith visible dimension times the jth latent dimension. If we replace this term here into the previous equation, then our gradient of loss with respect to the parameters becomes much simpler, much less daunting. However, this doesn't mean that it's actually easy to compute this gradient. In fact, it is not. The reason is that the first part is actually okay. We can simply substitute the data we already have from our training distribution. So basically we just sample an image and then we compute this term. To do that, we have to sum over our latent variables or sample from it after, as we'll see afterward. However, the second term here is very hard to compute. It corresponds to normalization or to our partition function, and it basically, here in the subscript, we see that it basically asks us to, sum over all possible combinations of images and latent dimensions. So basically, we need to iterate over all possible pixels and over all possible latent dimensions, and then start flipping them one by one in all combinations. This is, in fact, it involves 2 to the power of n plus d summations, which is clearly intractable for larger m and for larger d, so for bigger images and for bigger number of latent dimensions. It's exponential in complexity. This means that evaluating and optimizing our energy function and our probability density function thereof is going to take extremely long time. Actually, in most cases, or for bigger problems, it's probably not even possible. If we had just the anormalized part here on the left, it would be okay. But having the partition makes things extremely hard. Now, one way we can address intractability in this term is to note that this term stands for an expectation, so some sort of averaging. What one can do is then sample a lot of x prime and latent values from our probability density function, assuming that we know this probability density function, and take the average instead of computing analytically. So this is called, that's Monte Carlo sampling. So the problem here is, however, that how to even sample. I mean, we have a probability density function, but it's not like clear how we can generate new samples. It's not like a standard Gaussian for which there are known routines or the uniform distribution. So what we can do when we have when we want to sample from hard density functions is we can do Markov chain Monte Carlo, and for instance here we can apply Gibbs sampling. Gibbs sampling means basically that you're sampling one dimension at a time, conditioned on all other dimensions, and this process is guaranteed to converge, but it might take a very long time. So this actually is the second source of intractability. So although we can replace the analytic expectation with sampling, resolving our first source constructability, the fact that MCMC can be very slow, especially for high dimensional data, because of high variance, among other things. This makes it again intractable. So what can we do instead? Well, above here I rewrote my gradients as in the form of two terms, of two expectations again. So it's just simply rewriting, nothing different. The only difference here is that my first expectation, E of 0, stands for sampling from my training data, so like before, whereas E of infinity means sampling from my model. So in a way, I'm replacing my theta with an infinity symbol, and we'll see next why we do that. We do that for contrasted divergence learning. So to motivate contrasted divergence learning, we can revisit, or we should revisit, the maximum likelihood learning. Maximum likelihood training or learning means basically I want to minimize my my KL divergence between the distribution of data that I have, so what the training data I have, and the distribution that I am learning with my function P, right? Now, if you write this down, basically it comprises two terms. The first term doesn't depend on our parameters, on our model parameters, so when we're optimizing it, we can consider it constant, and because it's constant, it doesn't count for the optimization. So we end up only with the second term. What contrasted so this is what maximum likelihood does. What contrasted divergence does is something similar in a way. So the first term is exactly the same like above. However, it introduced now a second term, so basically computing the KL difference between our model, like sampling from our model, after n after n MCMC steps. Yeah, so measuring the KL divergence from the probability density function after n MCMC steps, and our final model. The final model is after getting a lot of, like, let's say, infinite number of MCMC steps. And with contrasted divergences, basically what we do is that we take the difference of the two divergences, and then we compute the gradients of that quantity, of the contrasted divergence quantity, and update the weights accordingly. So instead of using the maximum likelihood gradients to update our weights, we're using our contrasted divergence weights. Here, this is the expectation that we take after sampling for the nth time from our model. Now, if you were to do here the precise derivations, you would have some extra term or terms. These terms are small and can be ignored. Now, some intuition behind contrasted divergence learning. What it does, what it tries to achieve, is to make sure, as we see here, that it tries to minimize the divergence, the difference between divergences after from our training data versus n steps. So it basically wants to make sure that after n sampling steps, we're not too far from our data distribution. So usually just a single step, a single sample is enough, and in a way you can see this as minimizing reconstruction error. So given our data point x, we compute our posterior function p of v given x. We take a sample from it, like so, something not super like something like, okay, we can understand how this works. And based on our latent variable, we feed it to our second conditional. We obtain a new version of our input. So basically, we reconstruct our input now, and yeah, we sample from it like that. By comparing our original input and the reconstructed one, we can see how good or how bad our training is. The closer the two distributions are, the better. Graphically, this is shown in this picture here. So given our observations X, we first sample our latents, then we sample again reconstructions, and then we sample again latents. Usually a single step here is enough. And for RBM specifically, the contrastive divergence approximates the gradients by k steps of the Gibbs sampling. In the end, what it tries to do is it tries to push the nominator of our energy of the nominator of our PDF, so the exponential of the energy, and push the denominator. By doing so, it sort of encourages the model to obtain better, to have higher accuracy. Note here that because we assume independence between the x's, conditional dependence between the x's and between the latent variables, we can do parallel computations very efficiently, and that's very important. That's why we assume conditional independence. Now, how is the sampling done? Well, we mentioned previously Markov chain Monte Carlo with GIMP sampling. So basically, we have to initialize somehow, and then let's call this our x0 sample. It might be good, it might not be good, it depends on the type of initialization. Then we add up some noise, right? So from some noise variable, and we can compute the probability of that new sample, right? So x hat is our new sample here. If the score, that is the minus energy, is higher for our new sample, it means that that's good for us. It means that the new sample is even better, so we can replace it for the next time step in our Markov chain. However, it might be the case that by adding the noise, we arrive at a worse sample in terms of probability, and in that case, we don't immediately reject it. We still keep it. We can still keep it, but only with a probability that is equal to this exponential of the difference of the two scores. Now, since this is smaller than this is going to be smaller. A quantity smaller than 1. The further, the more unlikely, or the less likelihood our new sample has compared to, or the less the score our new sample has compared to the previous one, the more unlikely it is that we're going to keep it for our next sample. Now, after we do this, we go to step 2, and then we repeat the procedure till convergence. Because of this ratio of likelihoods, this means that the partition functions get cancelled out, and for our sampling, we don't really need to compute the partition function. Just having the scores from the denominator is good enough. Now, using RBMs was very interesting. So RBMs were some of the very interesting models back then. Back at the time, it was they comprised some of the first models to generate nice pictures, and also one could use RBMs for pre-training models and train them afterwards for classification. Following up on deep Boltzmann machines and restricted Boltzmann machines, on restricted Boltzmann machines, one can stack RBMs, assuming conditional dependence between layers, and then obtains deep belief networks, which are directed models. And if stacking the RBM layers are done such that there is no direction between, so there are connections from above and from below, effectively comprising a Markov model, then we arrive at deep Boltzmann machines. So we see here connections from both above and below. Now, because of exactly not having an order, this makes the information flow very complex. Therefore, it's not straightforward how to learn how to compute gradients. Computing gradients becomes intractable, and instead variational methods have to be used, or sampling methods and so forth. Thank you.